In this video, we're going to introduce the second derivative test, which, like the first derivative test, is a method for classifying critical values as being either local minima or local maxima. I'll say up front that I do not love this method. I pretty much always use the first derivative test, but it's classic material. And the reason we cover it in this section is that it's based on concavity. Suppose that f prime of c equals 0. So c is a critical value, and more than that, the reason c is a critical value is that the derivative equals 0, not that the derivative doesn't exist. Let's draw some local maxima that we might have in this situation. I mean, there's not a lot of variety going on here, right? A local maxima is a local maxima. And similarly, a local minima is a local minima. And if you look at these local maxima, concave down, concave down, concave down, concave down, concave up, concave up, concave up, concave up. The second derivative test, if the second derivative of c is positive, that is to say, this is concave up, then c comma f of c is a local minimum. And if f prime of c is less than 0, so we're concave down, c comma f of c is a local maximum. However, the second derivative test has limitations. It can fail. And that's not something the first derivative test can do. But if the second derivative equals 0, we get to know information. Also, recalling what I said earlier, This test can only be used to classify some critical values. There are local maxima and local minima where the derivative doesn't exist. And the second derivative test is not helpful for classifying those. Nevertheless, let's look at an example. In particular, we'll look at the same example we spent 3 videos analyzing. P of x is x to the 4th minus 4x cubed plus 10. This has 2 critical values. We've already done this work. And we already classified them using the first derivative test. But now, let's seek to classify them using the second derivative test. Well, we need the second derivative. 12x squared minus 24x. Can pull out the 12x times x minus 2. And let's try to classify the critical value at 0. But what a shame. When you stick 0 into the second derivative, the test fails. We get 0, and that gives us no information. When we plug 3 into the second derivative, our test does not fail. We get 36. 36 is positive. So that's a local min. When we classified this, we did use the first derivative test, and we found that 0 is neither a local max nor a local min, but you can't get that from the second derivative test. Let me real quick do 3 examples at once. F of x equals x cubed. G of x equals x to the 4th. H of x equals negative x to the 4th. F prime of x is 3x squared. G prime of x is 4x cubed. H prime of x is negative 4x cubed. F prime of 0 equals 0. g prime of 0 equals 0, h prime of 0 equals 0. So 0 is a critical value in each of these cases. And just using our knowledge of what graphs look like, for x to the 4th, this is a local minimum. Negative x to the 4th, it's a local maximum. X cubed, it's neither. But if we tried to use the second derivative test, we could take each of these second derivatives, and when we plug 0 into them, f double prime of 0 equals 0, g double prime of 0 equals 0, h double prime of 0 equals 0. So the temptation is to think that if the derivative being positive means it's a local minimum, and the derivative being negative means it's a local maximum, then the derivative being 0 should mean it's neither a local minimum nor a local maximum. However, as we see on this page, that's not true. The derivative being 0 gives you no information. Might be a max, I should say the second derivative being 0, might be a max, might be a min, might be neither. I will reiterate my opinion that the complications surrounding the second derivative test make it worse, frankly, than the first derivative test. That's just my opinion, though. Like if you're working through a test, I'm not going to tell you use the first derivative test or use the second derivative test. You'll have the options to use whichever test you want, with the qualification that the second derivative test might not work, in which case you'd have to use the first derivative test.